Good morning, Satish sir. Hello.
हॅलो गुड मॉर्निंग.
Yes, good morning, sir.
मी आणखीन एका पीसी वरून जॉईन होतोय. हा
सर
त्याला ऑडिओ नाहीये, त्याला ऑडिओ नाही, डोंट वरी.
हां हां तेच म्हटलं नाही
नाही नाही, ऑडिओ नाहीये त्याला.
इको येईल. हां
हा
ठीक.
हा
ओके
इमिडिएटली जॉईन होते आता. एट थ्री
ओके.
सेवन फोर सेवन नाईन सेवन 7052 7052 सतीश 1 2 3 4 5 6. लॉग बुकिंग क्या. I used it before.
Good morning, Jadhav sir.
एक मिनिट, एकच मिनिट. 1 3 4 5. मॅडम आला सतीश. हॅलो.
यस सर.
आलं का.
आवाज येतोय सर तुमचा.
येतोय ना. ओके ओके. हा ठीक आहे. सर एक मिनिट हा, एकच मिनिट.
उद्या उद्या सर एक 5 मिनिटांनी चालू करू आपण.
हा हा हा. Hello.
Yes sir.
Ah,
So will you please share your screen so that we will once check.
I will share my screen, पण ते ना
तुम्हाला co-host केलेलं आहे.
होस्ट केलं आहे. याच्यात हाऊ डू आय शेअर द स्क्रीन?
बॉटम सेंटरला शेअर स्क्रीनचं ऑप्शन असेल.
हो,
हा.
ते केलं and then share.
So either you can share your entire screen or the particular PPT.
Yeah.
Yes.
Now, can you see me? Yeah.
Yes. Yes.
Can you see this?
Yes sir. Yes.
Yeah. Yeah. So tell me, when do we start?
Sir, in just 2 minutes.
Yeah,
Participate.
sure, sure.
Yeah. Yeah.
Yeah, okay, okay. Your good name? Pranav?
Pranav Chipalkatti.
Okay, okay. And these participants are from, what are they? I mean, what is their background?
Faculties
Huh,
from
from? Of electronics?
electronics and computer, like mixed.
Mixed, okay.
Yeah.
Okay.
Mostly are from ANTC department.
Which one? Which department?
Electronics.
Okay, okay. And what is anybody connected with biomedical?
Few of them, those who are doing research.
Okay. And will you be recording this?
Yes, sir.
And will you send me a link after this? Recorded link.
Of the recording? Yes, sir. Yes.
Okay. And if the participants are asking question, we'll keep it at the end of the session, right?
End of the
In
session.
between, if somebody wants to type out a question, I will try to answer probably in between or maybe after the uh, presentation is over.
Sure, sir.
Or they can mail me. They can mail me the question. I will answer them directly.
Sure, sir. Sure.
Yeah. That light on, no? Okay. Switch plug लावा है ना? Yeah. Is it too much? Is it better with additional light or shall I remove this light?
It is better, sir.
It is better. Okay. Before we start, I suppose we are waiting for some more participants to join in. Pranav?
Yes, sir. Yes, sir.
So, meantime, the participants who are already there, if they want to ask me anything, they can ask me.
Sure, sure.
Yeah, nothing related to our presentation, but in general, if they want to ask me, they can ask me. Tell them.
Yes, sir. Participants are requested to put their queries in chat either, or you can unmute and have a word with sir. So we have our HOD sir, BD Jadhav sir.
Huh.
Yeah. Jadhav sir.
Then you, in that case, you call me Satish, not Jadhav, Satish Jadhav, so that there will be a confusion.
Yeah.
In HOD also Jadhav. I saw one more Jadhav there. So you call me Satish, please.
Yes, sir.
So I know you are talking to me.
Hello, Pranav sir.
Yes, sir. Yes, ma'am.
We can start, I think so.
Okay.
Yeah.
So with the permission, we'll start, sir.
Yeah, how many participants are there? Just huh? 27.
27.
Okay, okay.
They'll be joining, sir, in due course till they start.
No, but what is the time now?
10. 10:04.
It's a 10:04. We'll wait for 5 minutes because if they miss the beginning, just 5 minutes more we will wait.
Yes, sir.
I'll introduce you to my colleagues. He's too tall. He has to wait to come in front of the camera. He's Vivek Verma. He's doctor in biotechnology, so he has assisted me, and he will be sitting along with me to help me answer queries.
Yeah. Good morning, sir.
And I have Mrs. Usha, who's also going to help me to conduct this show.
Good morning.
तो स्क्रीन थोड़ा सा कर दो, then I can slightly. Yeah. Pranav, do you have other lecture after this?
Yes, sir.
What time?
11:45.
11:45. So there's a margin of half an hour. In case if I lose connectivity, Pranav, I will go on mobile on 4G.
Sure, sir.
Then you will have to take the in from the mobile. Okay.
Yes, sir.
Hope the connection will not go, but in case. The browser. Pranav, what is the background that you are having?
That is a today's banner, sir. With your
Okay.
yeah.
And you all these 10 days you are having the same topic, or it's only for today?
No, different topics
So
related to
all
AI and
but
biomedical engineering.
today is AI and biomedical.
Yes, sir.
And who else is going to talk?
So let me check. The second speaker is Kishore Bangale.
From?
He is assistant professor in Divapatli College,
Okay.
and the other one is Sudeep Thepre, Dr. Sudeep Thepre.
Okay. What is he?
He is a professor in computer department of PCCOE.
Okay. And what are the topics on other days?
So there are different topics.
But everything to do with AI only.
Yes, AI and biomedical.
AI and
Bi-
biomedical is today.
no, sir. The topic is AI in biomedical engineering. Applications of AI in biomedical engineering.
For all 10 days.
Yes, sir.
Okay.
Yeah. Shall we start, sir?
Yeah, we can.
Yeah. A very good morning to one and all. I, Pranav Chipalkatti, on behalf of JSPN's Rajarshi Shahu College of Engineering, Department of Electronics and Telecommunication, heartily welcome you all for the first session of Day 5 of 2 weeks Faculty Development Program on Artificial Intelligence and its applications in biomedical engineering. Today we have with us an eminent speaker, Mr. Satish Jadhav, to deliver session on topic Human Lungs and Supporting Equipments. I heartily welcome you, sir, on behalf of Department of Electronics and Telecommunication. I feel extremely honored to introduce him today. He is currently working as director at BioKit Private Limited, Mumbai. He has an extensive 40 years of experience in development and manufacturing of biomedical equipments and has conducted several training programs across India and abroad. We are fortunate to have you with us today. I welcome you once again and request you to start the session. Thank you.
Okay. Very good morning, friends. There is no way I can get the response. Zoom is a very odd platform to talk to so many people, but with the given limitations, we have no choice but to do that. I would have, uh, I would have definitely enjoyed talking one-to-one basis, but this is what we're going to do today. Pranav, am I loud and clear?
Yes, sir.
Okay. Everybody else is on the mute?
Yes, sir.
Okay. So we're going to talk about the artificial intelligence in the biomedical instrumentation. So we have to talk about biomedical instrumentation, and when we talk about biomedical instrumentation, we have to start our topic with our own body. Uh, Ultimately, I will be talking about a specific instrument. So I'll be talking about the specific body system, and that is a respiratory system. And in the respiratory system, I would be talking mostly about lungs. So in this introduction, I will ultimately come to the lungs of our body. Lungs of our body will gather oxygen from the air and give it to the different parts, all the parts, in fact, of the body. So we will start this way. I will give a brief talk on our digestive system and circulatory system also, without which this topic cannot be completed. So let us start with the digestive system. The food that we eat, is a fuel for our body. Without that, our body cannot work. When you want to do any work with your hands or with your machine, you need energy, and fuel will give you energy. And food is fuel for us. We run on carbohydrates and proteins. Petrol vehicle runs on petrol. Wood stove works on wood, and we run on carbohydrates and proteins. So food that we eat, carbohydrates and proteins, goes through our digestive system. It is digested, and in the process, it is broken down to small molecules of sugar and amino acids. And these molecules are so small that they are easily absorbed into the bloodstream. Now, this is packet of energy. Sugar molecules and amino acids are packet of energy that will be delivered to each and every cell of the body by the circulatory system, that is blood flowing in our body. When this food packet of energy reaches the individual cell, the individual cell will try to extract energy from this packet of energy. The mitochondria in the cell will break up the chemical bonds of these molecules, and the energy will be released. To release the energy from the molecules, the mitochondria needs oxygen to do that. I'll just give a small example. You have a piece of wood with you, you want to extract energy from it, you light a fire. You are combining that wood with oxygen, and the fire is lit, and the heat will come out as energy. Similarly, when we eat the food, that food has to be burned to release the energy. And burning, we all know, requires oxygen. And whenever you burn any hydrocarbon, the output is going to be carbon dioxide. So whatever food we eat goes into individual cells through circulatory system. The food is burned there. The energy is released. Energy is used by the body. Every cell is doing work, so they need energy continuously. And the output that comes out is carbon dioxide, has to be thrown out of the body. Now, digestive system is giving us fuel. The respiratory system is going to give us oxygen. And both these will ride onto the blood cells of the blood, and will be delivered to all parts of the body. So we need digestive system to give us fuel. We need respiratory system to give us oxygen. So to do this, to achieve this, we have two pumps working in our body. One pump, that is a blood pump, that will pump the blood throughout the body to carry these nutrients and fuel to all parts of the body. And second pump is the air pump, and that is nothing but your lungs. So friends, we have already come towards lungs, so I will start my presentation here. We're not going to talk about heart pump today, but we have to know this. This is the heart pump. Heart pump has right side and the left side, upper side and the lower side. So this is right upper, right lower, left upper and left lower. The blood from body will come to the right upper, will go to the left, the down right below, and will go to lungs for purification. From the lungs, the purified blood will come to the right, the left upper and the left down, and it will go to the body. This is how the schematic of a four-chamber heart, that is a pump. Please remember, it has valves. This valve here, this valve here, and this valve here. It has got four valves, and valves will make the flow unidirectional. Please remember this point. So a very efficient pump this is, and this is how, it's not a square type, this is just a representation. This is how the heart will look like, the schematic of the heart will look like. And this is how it is drawn, and this is how it looks actually. So this is the pump, this is the heart pump, which will circulate the blood, carrying nutrients and oxygen and other things. Now we have come to a second pump, that is air pump. There's some noise, Praveen. There's some noise. Praveen, there's some noise. Hello, Praveen.
Please unmute another participant's mic.
Yes, sir. Yes, sir. I've turned off.
Yeah. Okay. So we are going to talk about the air pump. Now we have talked about the blood pump. We're going to talk about the air pump. And we're going to talk about air pump in detail, not the blood pump in detail. Now remember, see this particular thing. This is an air bellow. When you contract this air bellow, the air will escape through this point. When you increase the volume of this air bellow, air would find rather an easier way to enter from here. So this is a valve here. So this is a slightly an efficient air bellow, where the air will come from here and air will go out from here. Now you look at this air bellow. When you increase the volume, air will come out from this point, and when you decrease the volume, air will go out from this point. So this does not have a valve. So this is not really an efficient air bellow. Unfortunately, our lungs are this kind of an air bellow. Our lungs do not have valve. I'm telling you all this because when we're going to talk about the supporting instruments, we have to consider this point. It's a rather inefficient air bellow. The air comes when the lungs inflate, that is when the volume is increased, the air will come from this point, and when the lungs deflated, or when they are contracted, or rather when they are relaxed, the air will go from here. So this is an air pump. That is what we are going to talk about, the lungs of our body. So we have this circulatory pump here. Both are mechanical pumps. We have this air pump here, and this is our body. The impure blood from the body goes to circulatory pump. It goes to air pump. The oxygen is mixed. It comes back to the circulatory pump, and it goes back to the body. So to have this, we have to achieve these three things: ventilation, diffusion, and perfusion. Ventilation is moving air in and out of the bellow, that is lungs. Diffusion is exchange of gases of oxygen and carbon dioxide. Remember one thing here, the diffusion will take place from the higher concentration to lower concentration. Diffusion will take place at two places. One in the lung, where the oxygen will be taken in and CO2 will be thrown out. And second, at the cell level, where the oxygen will be consumed and CO2 will be put onto the blood, which has to be removed from the lungs. So diffusion takes place at the two places, at lungs and at every cell. Then perfusion. Perfusion is pumping the blood through lungs. So only when we achieve ventilation, diffusion, and perfusion, we have enough fuel given to each and every cell of the body. If any of the pump fails, either circulatory pump or this pump, if any of the pump fails, the body might get nutrients, but may not get the fuel, oxygen to burn those nutrients. And the cell will come to the rest, and the body will also come to the rest in very short time. So we're going to talk about lung anatomy, physiology, and pathology. Physiology is a normal working of the organ. Pathology is abnormal working of the organ. Then we're going to see the life supporting equipments. Then we're going to go on to slightly a technical part of the discussion, that is block diagram of the supporting equipments. After that, we will talk about artificial intelligence, how we can introduce during, even while designing the supporting equipments. And to achieve this, we have to talk little about big data, how it is collected at the moment, how it should be collected. And if time permits, we'll talk about patient simulation and artificial intelligence in patient simulation. Let us talk about lungs anatomy, physiology, and pathology. Lungs, how do I, 1 minute, how do I take this down? No. Okay, this is slightly better. Okay, now this is our respiratory system. The respiratory system will take oxygen from the air and transfer it onto the blood. The oxygen in air is 21%. The other gases in air are nitrogen 78% and other gases 1%. So we anyway have a 21% oxygen in the air available. So normal patient at sea level may not need extra oxygen supply. Why did I say sea level? Because when you go at high levels, the air is thinning down, the oxygen content would be less. So you might need an oxygen support at the higher altitude. And if your air pump is not working properly, you may need higher level of oxygen to compensate for inefficiency of the pump. So let's see how our respiratory system is made up of. Nose, everybody knows, and the nostrils, yeah, everybody can see them. We can breathe through mouth also, and air from nose and mouth goes into an area called as pharynx. From there it goes to an area called as larynx, which is also called as voice box. Respiratory system not only helps us to gather oxygen, it also helps us to talk. Now I'm using my respiratory system to communicate with you through my mouth by controlling my tongue, my mouth, and the shape of my larynx. So larynx is called as voice box. After that is trachea. After that, trachea goes into two parts, left and right. This is called as bronchus, and we have a right side lung and a left side lung. Right side lung has 3 lobes and divided into 3 parts. Left side lung has only 2 lobes because this area here is required for our heart. Okay, and please see this. This is this red thing that is called as diaphragm. This is going to play a major role in operating our air pump, operating our air bellow. When you contract diaphragm goes down. When diaphragm goes down, the volume inside the lung increases and the outside air goes in. The diaphragm is relaxed, it will go up and the air will be thrown out. One more point to be remembered: inspiration or inhalation is a voluntary process. You have to decide, you have to order yourself, and you have to take your breath. Expiration or exhalation is involuntary process where the diaphragm is just relaxed. Our lungs, left side 3 lobes, right side 2 lobes, and you can see the heart, small heart sitting here. I'm calling it small heart because it is very small compared to lungs. Lungs has a capacity of 6 liters. 6 liters. You please in your mind, you please think about a 5-liter water can. This is more, 20% more than that 5-liter water can. A 6-liter lung. Okay, and the heart, it is enclosed in a rib cage, and it is also called, this area is also called as thorax. Thorax is the rib cage. This is a sternum, and these are all the ribs which are protecting our very critical organs, lungs and our heart. I see this beautiful, very beautiful diaphragm muscle, and when you pull this down, this is how the muscle is contracted. The area in these lungs is increased and the relative pressure goes low, so that will cause the air to flow. Without a differential in pressure, nothing can flow, either air, gas or liquid. There has to be a pressure difference. So this will cause a pressure difference. Contraction of the diaphragm will cause a pressure difference and air will flow in. When the diaphragm relaxes, the air will go out. This is a side view. So when you breathe in, the diaphragm comes down, the volume is increased, and the rib cage also goes out. The chest expands, and the air is in the lungs. So when diaphragm is relaxed, the volume is reduced, and the air will go out of the lungs. So this is breathing in. This is breathing out. This is the X-ray view of lungs. This is where they are situated. This is how they look like. We have already seen this picture before. And this is a trachea, then bronchus, then smaller vessels called air passage, not vessels, air passages called bronchioles, and every bronchiole will ultimately end in a small air sac called as alveoli. So every bronchiole will ultimately end in a alveoli. These are grapes-like things. There are 500 million alveoli in our lungs. I'm going by the figure that I find on various sites. You may refer to some people say there are 700 million. I would rather go as 500 million alveoli in our lungs. And if you see the surface area of all the alveoli, it is about 100 square meters. That is a large area required for perfusion, the oxygen for the gas exchange. Now, this is another section of alveoli. The impure blood comes from here. See this? These are all capillaries. Pure blood comes from here. By the time it leaves the alveoli, it has already become pure, loaded with oxygens. So blood comes from here. The CO2 goes inside and goes out, and the oxygen from air comes in, goes on to the blood. This is another bigger picture of an alveoli. From the your bronchus and bronchioles, it will comes to alveoli. The oxygen comes here and gets loaded onto blood, and the CO2 is offloaded. This is oxygen is downloaded and CO2 is uploaded from the alveoli, and it will go back from the bronchus to the trachea, the nose, and out of the body. Now this is a small cross section of a bronchus. This is a very healthy, nice looking bronchus. This is the air passage. What you see here is an airway. The air is going to come through this. And that is a ciliated lining of the bronchus, the small hairs. Whenever a dust particle comes into the bronchus, the wave motion of the ciliated hair, ciliated portion, the small hair, will throw that particle out. And that is when you will cough, you will sneeze, to throw that particle out. Now you see one nice normal lining of the airways. The muscles around the bronchus are also relaxed, so a lot of passage for air to flow. We are coming to the pathological side of the lungs now, that is abnormal working of the lungs. So this is normal passage, this is abnormal passage. Where the muscles are tightened, that reduces the airway passage, plus the swollen lining, plus excess mucus. The mucus is already, because will continuously exist in our bronchus, bronchioles, to trap the enemies. Who are the enemies? Enemies are virus, bacteria, dust particles. So they have to be trapped and thrown out. The mucus will do the trapping of these enemies, and the ciliated lining will try to throw them out while we cough. So this is a normal and this is abnormal. Now this is the very common, anyway we're going to talk about the supporting equipment. So we have to know not only physiology, the pathology of the equipment, pathology of the system. So this is chronic bronchitis. You must have heard of bronchitis very often. So this is the healthy bronchus. This is the inflamed bronchus with the excess of mucus. This is emphysema. This will happen where the alveoli are disturbed. Okay, this is more relevant in the patients who are habitual smokers. So So both these things will obstruct the airflow and exchange of gases, and the COPD is a very common lung disease. And this is pneumonia. Okay, this is pneumonia. Hey, there are two. Give to me. This yellow strips. Okay, this is pneumonia. We are under COVID-19 influence. So you know the limitations that COVID-19 has put on us. COVID-19 was initially called as, that is what causes the pneumonia now. COVID-19 patients suffer from pneumonia. It was called as novel coronavirus infected pneumonia. It was called as NCIP, novel coronavirus infected pneumonia. After that, World Health Organization renamed it to COVID-19. COVID stands for CO for corona, VI for virus, and D for disease. It is called as COVID-19, that is corona virus disease. The coronavirus, when it normally enters in our body through nose or through mouth, and it infects your lung, and the patient can suffer from a pneumonia, that is inflammatory cells and a fluid in air sacs. When air sacs are filled with fluid, the gas exchange cannot take place. So this patient suffers from lower level of oxygens, and then they are put on ventilators. In corona cases, about there's one more. About 15% cases become severe. Out of every 100 patients, 15% cases become severe. They have to be admitted to hospitals. Out of which 5% cases need to be connected to ventilator, a system called, we're going to talk about ventilator. And 4 out of 5 patients cannot survive because the pneumonia is sudden and very intense. So nearly 4% fatality is there for COVID-19 patients. In our country, it has come down to 2.5%, 3%. In some countries, it is as high as 7%. So we're going to talk about ventilator, how it is going to support. Ventilator, please remember, is only going to support you as giving extra oxygen, making your lungs more efficient. It is not going to treat your pneumonia. Pneumonia has to be treated with certain medicines. So patient has to be on pneumonia treatment plus ventilator for his revival. So all these pathological conditions of the lungs will put pressure on the lungs, and the lung capacity go down. We have a lung which is the volume of 6 liters. 6 liters. We don't use 6 liters at all times. What we breathe in and breathe out is only half a liter. So what happens to other 5.5 liters? It is remain idle. So this is a machine called a spirometer, where the patient will blow through this hole, and the spirometer will measure the flow, multiplied by time will give you volume, and spirometer will measure various volumes. This is the graph that will come out of spirometers. From here to here, it is 6 liters, and this is your tidal volume. This is just half a liter. Breathing in, breathing out, breathing in, breathing out. So you are told to breathe in as much as you can, and then you will get this extra inspiratory reserve volume. This is an extra volume that you can actually take in, but normally you don't. So when you take a deep breath, you can take in as much as this. You can actually take in about 2 liters of extra volume, which you normally don't. And then you exhale, then you breathe out, and as much as you can, then you can breathe out. You can come up to the breathing in and breathing out will be about 4 liters for a normal patient. With a pathological lung, it will not be this. So from this form, doctors can understand your lung capacity, and then of course you will take the blood test and other diagnostic equipment he will use, and he will treat you accordingly. So this is the spirometer, which will help you calculate the lung capacity. I will not go into details of each equipment, because if you have any questions, you can ask me right now after the session, or you can mail it to me. So we'll go to the supporting equipment. The equipments are of two types. One is the diagnostic equipment, which is this. This is a diagnostic equipment where we're going to diagnose the problem. And now we're going to talk about the therapeutic equipment. So we're going to talk about ventilator. We will talk about a CPAP machine. We will talk about oxygen concentrator. And this is again the diagnostic machine, pulse oximeter. We may not talk about pulse oximeter. If time permits, I can talk about ventilator, about pulse oximeter. So the therapeutic machine, that is ventilator. When you see the block diagram of ventilator, this is how it looks like. And it's become a very critical and useful tool in this COVID-19 situations. This is of course a microcontroller. It's controlling first of all the air coming from the atmosphere around it. This is extra oxygen source. It will control the valve. Suppose if doctor wants 21% oxygen only, then we cannot have extra oxygen. For some reason, wants 40% oxygen, then we can open this valve and combine the mixture, and we can confirm that the flow is there and measure the flow. So we are sure about the concentration of oxygen in the given volume. And say let us say 40% oxygen concentration, 60% other gases. Out of this, nitrogen is major gas. We'll go to this tank. Then the microcontroller, we open this inspiration valve, and this will be pushed inside the patient through the mask, or there can be a tube intubated inside this. The tube will go up to trachea, and the gas will go directly inside the trachea here. So there is no leakage. A full air can go to the two lungs. It need not come out through mouth. When you give it through nose, it can come out through mouth. When you give it through mouth, it can come out through nose. So the tube is put right here in the trachea. When the time is over of pushing, you have to give a time for a patient to relax. That is when this valve will close and this valve will open. The expiration valve will open. Again, the machine will confirm by the flow sensor that the air is going out. And this PIP adjustment is the pressure adjustment that we do not allow the pressure to come to atmospheric pressure, to maintain some positive pressure in the trachea. That is useful in case of pneumonia also, that alveoli are slightly inflated, so that the oxygen exchange can take place better. So you don't empty the lungs totally. You maintain some positive pressure. This is that expiratory pressure, positive expiratory pressure. So even after expiration, you maintain the pressure. That this will do that. At the same time, you are always monitoring the pressure and CO2 values in the patient tube, in the patient circuit, we call it. We have electronic circuit. This is a pneumatic circuit. So in the pneumatic circuit, always monitoring pressure and the CO2 for confirming the operation. So this is a simple, very simple block diagram of a ventilator. We will see how what we can do to have artificial intelligence in this ventilator little later. Now this is a CPAP machine. CPAP machine is required for the patients. I'll just go back to slide 1. You see, this is a mouth, and can you? This arrow is not seen there, no? Huh? No, but when I go here, the arrow is not seen because this thing comes. How do I do that? How? Down. Yeah. Okay. Now, can you see my arrow? Huh?
Yes, sir. Yes.
Okay. Yeah. So this is the nose. This is the mouth. Air can come either from nose or from mouth. It goes here, and this is a windpipe. Okay, this is a windpipe, and this is a food pipe. So when we eat, this windpipe has to be closed, and the food should go here and not here. So you see this is a narrow opening here. Can you see that? This is a narrow opening here, So because of the aging process, the muscles become little loose after the age of 40, and this one falls back when you are sleeping on your back and facing the sky. Okay, this falls back, that will close this passage. Then the patient, that particular person starts snoring, because this will vibrate when you take the breathe in or when you breathe out. This will vibrate. The snoring is an indication that first of all it's aging, and second, this muscle has become very weak. So as a result, in extreme case, this becomes passage becomes zero. So there is total blockage of air. So in that case, patient goes in something called as sleep apnea. Apnea means cessation of respiration, and sleep means normally it will happen when the patient is sleeping. So patient will not get oxygen for some time. His brain will wake him up. He will get up. He will take a desperate breath, and again he will go back to sleep. And same thing will repeat. So for such patients, this machine is used. This machine is used, which maintains the positive pressure, continuous positive airway pressure, that is a form of CPAP. It maintains a positive pressure so as to keep that air passage open. This is a simple block diagram. Basically, the pressure is maintained by this blower motor, which is going to the face mask. The motor driver is controlled by the microcontroller. And you're measuring pressure here. This feedback will tell what the pressure is, and microcontroller will maintain that pressure continuously during your respiration. So this is the block diagram of the your CPAP machine. We will see how what intelligence we can introduce in this CPAP machine little later. This is oxygen concentrator. This is a machine which will supply oxygen. All these machines have become very relevant in COVID-19 cases. People are dying to buy these oxygen concentrators, and they are. You can buy them. You can take them. You can hire them also. Some patient, because it is only for some time. So if you go to buy these oxygen concentrated, it will cost you around 35,000 rupees, and they take about 1,500 rent per month, or 2,000 rupees rent per month. So you can hire them and keep it at home for if you have a COVID patient at home. So what it does is, see, air is oxygen. Oxygen in the air is already 21%, and nitrogen is 78%. You remove the nitrogen. Just remove the nitrogen, so the air that comes out becomes 90 to 95% pure oxygen. So this is what this machine does. It traps the nitrogen, and so it allows the oxygen to pass through. So it becomes 95% oxygen, and this can be given to the patient with a face mask similar to this. You have to sleep with the mask like this. With your, or you can connect oxygen cylinder instead of oxygen concentration. Oxygen cylinder, then you have to have a replacement cylinder when you want to change it. And oxygen concentration works on the main supply, so you have to have a battery supply, battery backup to for the continuous supply of oxygen. Otherwise, if the main circuit fails, patient will suffocate. And this is the pulse oximeter. We will not talk about it right now. If time permits, or if somebody has a question, we will talk about this. Now let us talk about artificial intelligence and the big data. What is the time now? 10:45. So another 15 minutes. Let us talk about the artificial intelligence and the big data. This is a typical biomedical instrumentation. Let us say IoT based biomedical instrumentation where Raspberry Pi is used, and you are monitoring heart sound, blood pressure, pulse rate, and camera, and all this information is uploaded in the cloud on the internet. That can be downloaded in your smartphone. That can also be downloaded in doctor's smartphone. Doctor is sitting here, and doctor will give you advice, and accordingly you can take action. So this is uploading of data. Now whatever data you are uploading can remain there, for a future reference, and for studying of history, and for the development of the analytical software later on. So this uploading of data. Right now, uh, only physiological parameters such as ECG, pressure, pulse rate, temperature are monitored by this device, and that data is being uploaded. This is for a diagnostic machine which will analyze the patient. If you come to a therapeutic machine, that the machine which is treating the patient, right now this data, up to my knowledge, is not being uploaded. Where the patient signals are there, physiological signals are there, like blood pressure, oxygen, your temperature, your ECG, all those signals are there. Plus the machine is giving some dosage to the patient. In ventilator, you are giving dose of oxygen. Some other machine will give some other dosages. So you are treating the patient. This is a therapeutic device. But in this machine, both the all three, like your physiological signals, the dosage that you are given, and your control unit settings should be uploaded. Right now, I don't know, or I don't think it is being uploaded, and it can be stored in the cloud. So this will help us for a better design of the therapeutic machines. This particular thing will help us in better designing of analyzing machines that will analyze the patient's waveform and categorize them whether they are normal or abnormal and the magnitude of abnormality. They can do this. Whereas this machine will tell us how the patient's history was, and after giving so many doses, how the patient improved, how the biological signals improved. So this uploading of this data is very important in the near future, because as you go on pumping in data, only time will make this data a big data. You cannot have a big data right in the beginning. So this has to be started as early as possible to make it a big data one day. Now we'll come to the designing of medical equipment. This is for any other equipment, including medical equipment. Basically, you have users need. In our case, the patient needs oxygen. Then the engineer will design the inputs. Then it will design process how the signals will be processed, and he will check the output whether the desired output is there, can be verified through this, whether the output is as per the design input. And then you make a medical device after this designing, and then you have to validate the design as per the instrument need. The patient needs. The patient needed oxygen in a particular form, whether this medical device is fulfilling that requirement. And this is reviewed. Every stage of the development is reviewed. This is in-house. This is in-house. The outside world doesn't know what you are doing. Okay, but as far as the big data is concerned, so even when the patient is being monitored in the hospital, it is right now in-house. The outside people, the outside world does not know what is happening to that patient. So patient's data, for a data to become a big data, patient's data has to be uploaded. It is happening. The norms will be set by the authorities, and as per the norms, the data will start streaming up, and then the data will become a big data. So even for make even the designing process, which is in-house, the outside world is not aware of this your designing process. Very soon the outside world will have to know how you are designing and how reliable your machine is. For that, you will be compelled to upload this review of all the stages up and then down. So you can take a reference from this uploaded data by the other designers, and your process can improve. Your process can enhance this data so that furthermore the processes of the further designs can improve. So data will go on becoming bigger and bigger. To start with, it is smaller, then it will go on becoming bigger and bigger, and it will attain a critical mass. When this data attains a critical mass, it can be used for downloading and assessing your design systems. Now, let us see how we can incorporate artificial intelligence in a particular instrument. Let us see ventilators. Now, ventilator gives an alarm when the system detects that the patient has crossed, patient parameters has crossed limits. So instead of detecting and giving an alarm, it should have a predictive analysis. The instrument should have a predictive analysis so that the progression towards alarming limit is detected. And once that is detected, instrument on its own can take an intelligent decision, or it can look at the cloud and compare the data in the cloud and come and take an intelligent decision for readjusting the alarm limits. But then it has to intimate the operator, could be a nurse or a doctor, about the readjustments. See, what happens is ventilator is a very critical instrument, and to be very frank with you, if the settings are wrong, instead of helping the patient, you will kill the patient. So you need an absolute intelligent operator around the machine, and the machine is being connected to the patient, which he cannot be all the time. Even in one ICU, there are 7 ventilators. An intelligent doctor or an intelligent nurse cannot be around all the time in front of all the patients all the time. So we have to make the machine a little more intelligent than what is now, so that the machine will make its own decision and intimate the operator, a nurse or a doctor. The second artificial intelligence that we can put in the ventilator is right now the patient's effort, like this ventilator has to support the patient. If the patient is in total anesthesia, ventilator will keep on giving the bolus of air, oxygenated air to the patient, and patient can remain alive for months. But that is not the intention. Intention is to revive the patient, bring him out of the ventilator. For that, the machine has to see whether there is any effort from the patient for revival on its own. So when the machine detects that there is an effort from the patient, machine should assist the patient accordingly. Right now, the detection of the patient's effort by the machine is on amplitude basis. Machine will decide. I will just go back to this block diagram here. We are measuring pressure here. Oh, we are measuring pressure here. When the patient is so one bolus of air is already given to the patient, and machine wants to see if the patient is making any efforts, and if he makes an effort, you will see a negative pressure here. When we breathe in, we actually create a negative pressure in your lungs. That's how the air goes inside. So the negative pressure is sensed here. That's how the controller will know that patient is making an effort, and it will help the patient accordingly. So here, these patient efforts are now detected by way of amplitude. How much is the pressure? Okay, it is about 3 centimeters of water was the attempt made by the patient, but we want 4 centimeters of water pressure to be detected as an attempt. But it's my suggestion, it's my view that a wave shape of that effort has to be analyzed. Today, ventilators are not analyzing wave shape; they are only analyzing amplitude. So, wave shape has to be analyzed, and for analyzing wave shape, you have to look at the big data. Without looking at the big data, you cannot write an algorithm which will confirm the wave shape and the amplitude, and then categorize it as a patient's effort. So big data will help us to introduce this intelligence of analyzing the patient efforts. Now, the third part in ventilation works basically on different modes. The two simple modes are either you give a preset volume of air to the patient, or you get a preset pressure for some time to the patient. When you are giving preset volume for a given time, you are giving a constant flow. Say you are giving at say 5 liters per minute for 0.1 minute or the 6 seconds. That is, you are giving half a liter of air. Now it is given at a constant flow. Why should it be given at a constant flow? What you can do is you can check the pattern of the flow, because the flow will also depend upon the opposition by the lungs. Like our electric current depends upon the resistance or the impedance, the flow of current. Here also, the lung will have its own resistance and impedance. That impedance is called as compliance of the lung. That compliance of the lung in a normal patient and abnormal patient is different. So machine has to look out for the compliance, look out for the resistance, and then understand the pattern in which the flow is to be given for the comfort of the patient. Right now, the constant flow is being given. I suggest, my views are that the flow pattern has to be understood and flow has to be adjusted accordingly for giving the preset volume. That will make the machine more intelligent. The second mode is, and here the problem is when you give a constant volume, if you give more volume than the lungs can withstand, the pressure will go on increasing. So when you are giving a volume mode, you have to constantly look out for pressure and be alert if the pressure should not go up. So in the pressure mode, you are giving a constant pressure. It's like giving constant current or constant voltage. This is a constant current source. This is a constant voltage source. So when you are giving a pressure as a constant voltage source, like a constant voltage source in our electronics, you have to be worried about the volume. When in volume mode, you have to worry about pressure. In pressure, you have to worry about the volume. That in a constant current source, you cannot have more voltage. In constant voltage source, you cannot have more current. So here in the pressure mode, you cannot have more volume. So you have to check for that. So here also you can, instead of just giving a constant pressure, you can study the flow pattern of that patient and modify the mode. So this is how instead of stopping a predetermined action, it can modify until until it is controlled by the your operator. Until there is an intervention by the operator, you have to do that. And operators are not always available next to the machine. So if you make the machine more intelligent, then you may have a better effect of effect in helping the patient and taking him out of the ventilator ultimately. This is how AI can be introduced in ventilator. Now, air can also introduce in CPAP machine. The CPAP machine gives continuous positive airway pressure. The pressure in the patient's respiratory system is not allowed to come down to zero or equal to atmospheric pressure, but to give continuously positive pressure. Now, that positive pressure is decided by the doctor. He tells the patient, okay, when you go to sleep, adjust this pressure limit and go to sleep. But that pressure limit may not be required at every day at the same level. It will be required differently at different time, different days, and different patient positions and different patients' emotional setups. All that has to be considered. So we can now have a feedback taken from the patient. For example, breathing, sound of breathing. If patient starts snoring, the machine can increase its pressure limit till the snoring stops. So it did not a preset value. It can be dependent on the patient's requirement. Even when patient is sleeping on his side, accelerometer sensor can be used to detect the position of the patient and accordingly adjust the positive pressure. So instead of giving a constant positive pressure, machine can be made more intelligent by changing the pressures as per the patient's requirement. And the last we will discuss is the oxygen concentration. Right now, what is happening is patient will buy, patient relatives will buy an oxygen concentrator up to 15 liters per minute. And they will adjust some respiratory flow, the oxygen flow to the patient. Now, if the machine is on battery backup, your battery life will depend upon the flow rate. The more oxygen that you flow, the battery will consume faster and will not last longer. So we can introduce intelligence in that system which does not exist as per my knowledge today, that you can give a feedback from your pulse oximeter and adjust the flow rate accordingly. If more than the required flow rate need not be adjusted. Okay. Then when the patient is breathing in, you can adjust you can increase the flow rate. When the patient is breathing out, you can decrease the flow rate. So you can save the motor consumption and you can make the battery last long. So these are some of the intelligent that can be introduced in the supporting machines for the respiratory system, that is lungs. Now about the big data is being sent right now. They are all diagnostic big data only, like which medicine was given, what was the blood count, and how much was the blood pressure, and what was the pulse rate, and it goes like this in the cloud. This is not a structured data. Now we have to have a structured data in the cloud, so that we can make the best use of this data. This will happen when the respective authorities will work together. Now, so improving health through data science is nothing but we have to have our vision so that every healthcare interaction that we do or research that we do should be aimed towards enhancing access to large scale data and advanced analytics. Thank you very much. I am ready to answer all the queries that you may have. And if you want to ask the queries later on, please write down my email ID info@biokitindia.com. This is my contact number. You can ask me questions now, or you can ask me questions anytime.
Thank you, sir.
Yeah, there are a couple of questions.
I request Dr. Santosh Vagas, sir, to continue with
Yes,
the
sir.
question answer session.
Uh, Hello, sir. Good morning, sir.
Good morning.
Sir, myself, Dr. S.C. Vargas,
Yes.
Assistant Professor of ENTC Department of Rajarshi Shaw College of Engineering.
Okay.
Sir, some questions from audience.
Yeah.
Question number one is, suggest any indispensable books, websites, tutorials, or any reference material for design and development of embedded hardware used for medical devices.
The question looks very small, but we'll have a big answer. So I do not have the answer right away in front of me. I'm very sorry, but I can ask me this. You mail me this thing, and I will try to give this, because this not just one site that I can refer or one book that I can refer. So ask the queries. Yeah, mail it to me. I will try to answer that on the email.
Okay, sir. Okay, thank you, sir.
Yeah.
Sir,
Oh, he's reading it. He's reading it. Yeah, tell me, sir.
Sir, another question is there any simulation tool available to simulate the medical device prior to its hardware?
Uh, it, um, uh, 1 minute. Yeah, if you see this, we design, manufacture patient simulators. We do design and manufacture patient simulators, and our the latest project that we are doing is we are manufacturing a lung simulator, designing a lung simulator, and that simulator can be used to check the machine or training the operators. Right now, the simulators which are available, which we sell, they are only very high-end simulators. The simulators will cost around 1 crore. So right now that is available, but we are trying to make a low-cost simulation device that will help in designing, help in training, and helping studying the understanding. So medical and engineering students has to use this simulation device for studying. Then design engineer has to use this simulation device for designing his equipment, and doctors has to use this device for training the patients, training the nurses. We have this. We have this. I do not know what the question was. Whether there is a device available.
Yes, sir.
So this is in the making. This is not yet available fully.
Yes. Okay, sir. Okay, thank you, sir. Thank you very much, sir. Okay. Good morning, one and all. I, Dr. S.C. Vagas, on behalf of Rajarshi Shaw College of Engineering, Katodi, Pune, extends a very hearty vote of thanks to dynamic personality Mr. Satish Jadhav for giving his valuable thoughts. Sir, thank you very much for exploring lungs anatomy working in this pandemic situation.
Yes.
This information is very important.
Yeah.
The coronavirus also related to these lungs.
Yes.
After that, sir has explained the respiratory system of human body and spirometer calculate the capacity of lungs. Then microcontroller-based ventilator, microcontroller-based SCAP machine, then oxygen concentrator flow diagrams, then artificial intelligence in ventilators, CPAP, and AI in oxygen concentrator. Okay. Uh, Thank you, sir. This session was very informative in this regards. Thank you
Thank
very
you.
much, sir.
Thank you so much. Thank you so much.
Thank you.
Thank you all.
Hello.
Thank
Hello,
you, sir.
Pranav.
Yeah. Thank you, sir. I'll be mailing you the recorded sessions link.
Yeah, and the participants' ID if possible. Do you have that? Hello, Pranav.
Yes, sir.
You mail me the link and also the participants' information. Who all have participated and their email ID.
Yes, sir. Yes, sir.
Okay, and
Yeah.
give my email ID to everybody.
Sure, sure. Sir, is it the same info@biokitindia.com?
Yes, it is.
Okay, thank you, sir.
Yeah, thank you very much.
Thanks a lot, sir, for giving me your time.
Yeah. Hope you have enjoyed this session,
Yes, sir. Sure.
and we will meet again. Thank
Yes,
you.
yes, sir. Thank you, sir.
So he is not yet logged out. Can I log out now?
Yes, sir.
Okay.
Yeah. Participants are requested to remain in the session. The next session will start soon. Thank you.